one, and action.
Werner. Today we are exploring the concept of how complexity grows from simple origins. Can you tell us more about it?
Many of our original services have the moniker simple, like S3, the simple storage service. Simple may be in the name, but the reality is by making things simple, they can be terribly complicated.
In this episode of Simplexity, we tell the story of one of the world's largest storage systems and the team of innovators working to keep it simple.
You know, it was back in the early 2000s. There were, I think, 4, maybe 5 of us. Me, Werner, Al, a few others that they're just not here anymore. It was a REST API and a handful of features.
So Alex inspired lots of the simplicity behind S3, right?
Alex, the pizza guy.
Al?
Al.
Alex?
Alex.
Alex? Hey, welcome.
As usual, Werner, he saw something in him that no one else did.
I think he really appreciates my approach. I'm all about keeping it simple. Just, you know?
This one night, we'd ordered some pizzas and
He comes in, he's holding this stack of pizza boxes, you know, like 20 feet high.
Oh, God, I think I know what this is. Something different. What is this?
He trips onto the ground, drops most of the pizzas, whoa, and he utters the words, 2 pizzas per team, I guess.
he managed to save 2 pizzas. Good on him. And we developed 2 pizza per team.
The two-pizza team. Yes, we broke down our functional hierarchies and restructured the organization into small, autonomous teams. Small enough that we could feed each team with only 2 pizzas.
Together, we make 1 pizza.
Oh, plus Jeff and Kevin, 2.
2 pizzas per team. Yeah.
Or back when we were looking at ways to reduce storage costs.
I devised this very simple plan.
And Alex just shows up with a pizza cutter and he starts sharding the slices.
Right now, I'm working on the Franken pizza. It's a fritza.
Boom. Welcome erasure coding. We had to rewrite our entire storage engine. Well, he had to.
Yeah.
Did you hear of the glacier incident? Alex kept making people put half of their pizzas straight into the freezer. And there were so many leftovers. So many leftovers.
Can you tell us about the glacier incident?
Glacier storage classes, you mean? Different cost tiers for different access patterns. We're always looking to keep things simple for our customers, no matter the complexity it adds for us. This is just something we have learned to live with, embrace, cherish even.
Who really knows if Alex sparked all of these innovations? He became part of the furniture.
Ooh, that's pungent. That's 2016.
Here he is. This is the guy. This guy loves you.
What? What? What's up, Alex?
So all this success was fueled by the humble pizza.
Pizza? I thought this was a documentary about complexity and simplicity.
Yes, absolutely. In fact, we have your long-term collaborator here, the maverick who you hired to inspire simplicity. Alex.
Werner. Oh, great. This is fantastic.
Who the f*** is this guy?
Didn't you hire Alex? He inspired the 2 pizza team.
Alex?
Alex.
Al. I told you to get Al. LV, the main developer on S3 in the early days.
Concord that, please.
Please welcome the Vice President and CTO of Amazon.com, Dr. Werner Vogels.
morning. I don't know, every year I get more humbled by your enthusiasm. I hope I can meet your enthusiasm of queuing here at 6 a.m. in the morning already to come and hear my stories. I hope I can live up to those expectations. This year has been a bit of a special year. 20 years ago, a not so young kid of 45 decided to give up his academic career to go work at a bookshop. Yeah? And if you would have asked me in those days if I would ever work for 20 years for the same employer, I would have carried you off to the insane asylum. But 20 years at Amazon is just mind-blowing. Every year has been different, and the amount of technology achievements that we've made in those 20 years are just, I don't know. I still can't believe it. And I'm not done yet, either. Yeah? Now, one of the things for those 20 years has been continuously learning and learning and learning. Because actually, as an academic, I didn't really know what I got myself into. I may have thought that in academia I was building systems for real people, but to be honest, I never had to deal with customers. I never, there were some really hard-learned lessons with respect to that. I really needed to get my head around it. But learning and learning and learning was definitely something I did over the past 20 years. I was so gung-ho, so full of energy, so opinionated, and so arrogant, to be honest, in those days. Yeah? But my academic background really hadn't really prepared me that well for what was about to come. The luxury academic assumptions like machines fail by stopping, or failures are not correlated, turn out to be completely unrealistic. And when a few months into the job, Jeff Bezos and Rick Dalzell asked me whether I wanted to take the CTO job, I really couldn't pass up the opportunity to build the world's largest distributed system that was going to be used by almost everyone. Alvin Mullen, who was the CTO at the time, he didn't want the job. He didn't want the job. And he really wanted to return to being an engineer and hand code sort of the next generation of technology. And we should be extremely grateful for Al, because he built the foundation of AWS. All the hardcore technology behind the scenes have been off his hands. And the technology culture within AWS is definitely something that you see Al's fingerprints all over. So I had really big shoes to fill. But given that actually nobody really knew what the CTO job entailed, my arrogance got the better of me, and I did take the job. Now, in those 20 years, there's been a lot of highlights. Yeah? And one of them absolutely was the first reInvent. Because I got the opportunity to talk to you and to sort of lay down principles of what I thought was going to be the next generations of development. How we are going to radically different build these applications in ways that we've always knew we wanted to build, but just never could. And so, in this first presentation, I laid out sort of 4 different categories in which I think I gave you advice. And now, why don't we take a quick look back at it? How well did all of this turn out? I think some of them went out really well. I'm really proud that many of you are running your production workloads in at least 2 AZs. And I think continuous integration and continuous deployment and things like that, everyone's doing that today. Not necessarily because I told you to, but I'm very happy to see that those things made it into everybody's package of development. There are a few things that were maybe a little bit more controversial or took a bit more time. Decompose into small building blocks. Loosely coupled, stateless. At Amazon, this is something we've been doing all the time. And it allowed us to scale and be reliable and evolve pieces independently and things like that. However, it was stepping in the middle of some form of religion. Whether you do monoliths or services or microservices or nanoservices, all of these seem to be so controversial. Yet, architecture is something you do based on the requirements that you have. Or maybe sometimes, you do it based on the technology you decided to use. It is very hard to build a nano or microservice if you run over Rails. And as such, you automatically choose for a monolith. So I wrote this article on all things distributed, sort of laying out what I think are the differences between monoliths and microservices and what you do in this particular scenario. Another thing that I suggested that you do is work with the business. After all, we don't build technology just for ourselves, just for us as technologists. We build it for customers. And whether those customers are internally, your business, or they are really your customers externally, you build it for some reason. And as such, you need to collaborate closely with the business and build your architectures in such a way that they can have control over that one way or another. I gave you advice to break up your applications into tiers, then have a conversation with the business. For example, how reliable should each of those tiers be? Now, of course, the business will say everything needs to be 100% reliable. And then you explain to them how much that will cost them, and then you can have a conversation. Yeah? And definitely, that point that I said, now we can architect with cost in mind, was blatantly ignored by everyone. Yeah, because suddenly, you could do all these things. You could move so fast. You were no longer constrained by sort of the physical hardware in your own data centers. And it wasn't until last year that we really saw a desire to sort of start to think and integrate cost into your architectures. And I hope that last year's Frugal Architect actually gave you some guidance in that. Actually, we've been revamping the Frugal Architect website with a lot of new content, very deep content from a number of engineers, how they've been applying frugality in their work, a number of podcasts as well. If I look then over at the resilient part, there is this famous quote that always gets attributed to me. Unfortunately, the quote is always incomplete. It's not just everything fails all the time. The most important part was actually the second sentence. So plan for failure, and nothing will fail. Survival isn't something that you leave to chance. You have to plan for it. So looking back at that first presentation, I think many of the principles still hold. Although I probably would add a few things to today. Now, evolvability, definitely the ability to accommodate changes over time. And probably, how do you choose your database? I mean, in 2012, we didn't have that terribly much different choice. But now with the whole range of purpose-built databases, you probably need some guidance around that, what to use in what particular case. However, there was one thing in 2012 that I clearly hadn't fleshed out yet. In those days, I presented it to you as Occam's razor. Yeah? Objects should not be multiplied beyond necessity, for those of you who didn't get Latin in high school. What I actually really meant was to keep things simple. Yeah, the KISS principle, keep it simple, stupid. I don't know why that stupid is at the end of that, because I don't think you're stupid if you can't keep it simple. Because complexity sneaks in all the time. Yeah? And it's something that you really need to take into control. You need to think about how to manage the complexity. And indeed, complexity for many of us is inevitable. Systems become more complex over time, which is a good thing, because in general, we're adding more functionality to it. We need to scale. You need to address security issues, all of these kind of things. And AWS, remember, many of the AWS services are still called simple. Simple DB, simple storage service, simple queuing service, simple notification service. None of these services are simple under the covers anymore. They're all really complex. But we, for some reason, managed to achieve that. We managed to manage the complexity. And many of them have achieved this complexity very successful. There's some stumblings along the way, though. But we managed to manage complexity the hard way. And I'd like to spend today actually talking to you about the evolution of these complex systems at Amazon. How we do it safely, securely, and simply. Simplexity. Yeah? Complex systems built against simplicity principles for manageability. A very relevant law in this context is Tesla's law. Yeah? Conservation of complexity. Complexity can neither be created nor destroyed. It can only move somewhere else. And interesting was actually that Larry Tesler was at Amazon when I joined. And I learned a lot from Larry. He was mostly concerned about user interfaces and the functionality behind it, what you expose to your customers. But it was really fundamental to think about that, complexity is a given. However, not all complexity is created equal. Yeah, there is clearly intended complexity. That's the kind of that's necessary. Yeah? It helps systems scale, adapt to new features, meet changing customer demands. Yeah? And it's intentional, and it serves a clear purpose. But then there is the unintended complexity. Yeah, the kind of that sneaks in, often through changing technologies or a lack of architectural oversight, and it slows you down and it makes systems harder to maintain. The key is to recognize both types. And if you don't, your systems quickly go from flexible to fragile. So what are the signs of unintended complexity sneaking in? Yeah? You all know this. I mean, we've all been here. Declining feature velocity is definitely something. If I look at Amazon, when we went from monoliths to services, and from services to microservices, and from microservices to shared services infrastructure, every time the key there was, the driver for that was that we saw that innovation was slowing down. That the kind of hard things, the behind-the-scenes things that we needed to do, made it harder to implement the next features. But you all know this, frequent escalations, more and more tickets. The code base is so big that actually nobody understands what's going on. And so all of these patterns actually get in your way of making progress, of keeping the system flexible but reliable at the same time. And so a good example of how complexity moves around, that you can't sort of escape it, is this particular example. This is sort of an abstract way of how I think about customers and AWS. So customers will have an application loader, they have a bunch of domain-specific apps underneath there, and all of that runs over AWS. Now, most of our customers actually implemented some foundational services, some shared services that actually are domain-specific but shared by each of their applications. We always work with our customers to look at sort of the complexity in the shared services layer. Are there things that they have to do because we didn't make it simple enough for them? Now, one of those things is absolutely eventual consistency in Amazon S3. We launched with that because in 2006, there was the prevalent thinking about that was the only way that we could make systems reliable and survive failures. Many of our customers, however, found it very hard to deal with that. You may have created a bucket, and then had to do a write to it immediately, and it would turn out that the bucket wouldn't be available yet. Yeah, not a good customer experience. So many of our customers tried to implement strong consistency over S3, which was risky, because implementing strong consistency is, first of all, hard, but it's also making sure that you catch all the edge cases. And so the right thing to do there was not to remove that complexity, but to move it where it should be. So we implemented Amazon S3 strong consistency inside S3. It's moving the complexity to where it needs to be. And by the way, it's also the right place to be, because we could use automated reasoning to prove to ourselves that actually everything was correct, that every edge case was being handled. Now, I'm not the only one, of course, at Amazon that Amazon's not the only one that actually handles complexity in that particular way. You all deal with complexity. And there's a reason for it, because our applications continuously evolve over time. There is a need for that. Now, many of us, if you look at sort of these signals of complexity, there is one signal that often is understood wrong. Where many would think that complexity is the number of components in the system. That's not the case. It's absolutely not the case. Because counting components doesn't necessarily mean how chaotic your system is. And there's a great analogy by Paul McCarthy that I love, actually. If you think about riding a bicycle, in this particular case, think about the simplest form of cycling being that of a unicycle. It's simple, very limited number of components. And if you can master riding it, it is amazing. You can turn on the spot. But it's really hard to ride one. And just counting the number of components isn't a measure of the overall simplicity of the system. Now, you can also take a tricycle, which is very easy to ride. You won't fall off that easily, but actually most of us learn how to ride bicycles on a tricycle. But it doesn't give you much flexibility, because turning corners is actually pretty hard on one. So the ideal solution for cycling is that of a bicycle. It is more complex in the number of components, but it gives you great flexibility. Now, master it is harder than riding a tricycle, but definitely much easier than riding a unicycle. And it's the overall experience that signals complexity. A bicycle has more components, but it is the simplest form from a holistic point of view. And believe me, if you look at the place where I grew up, bicycles are everywhere. And yes, we do package delivery in Amsterdam using bicycles, and the Postal Service actually delivers your letters at home using bicycles. If you think about simplicity, it isn't accidental. Keeping things simple while adding complexity requires discipline. If the design makes sense to a team that is not part of the original design team, it's not really a pretty good sign. Now, there is one company that I really admire in terms of keeping things simple while hiding tremendous complexity under the covers. And let's hear from that company now. Please welcome the CTO of Canva, Brandy Humphries.
Thank you and good morning. Canva was founded over 10 years ago with the mission to empower the world to design. We've built a product that makes it easy for anyone, regardless of their skill level, to create stunning visual content at scale. Today, Canva is used by more than 220 million users in 190 countries to create and collaborate on everything from presentations to videos to whiteboards and more. But we're all engineers here, so please allow me some vanity metrics. Our platform handles about 1.2 million requests per second. We have over 162 petabytes of media under management, and that's growing by about 230 terabytes every day. To date, we've had over 30 billion designs created, and our users are adding over 450 new designs every second. But I want to take you all the way back to the very beginning of this journey, when most of these numbers were very close to zero. I joined Canva back in 2014, when there were just a handful of us. Here you can see most of the back-end engineering team back then, and around this time, we're in a single room, it's cheap rent, and there's a dodgy fuse box. And in winter, we could choose. Do we run heaters, or do we have external monitors? And naturally, we chose monitors, and we adapted. And I took this photo around this time of me literally coding in fingerless gloves because it was so freezing. Now, top of our minds around this time was the architectural quandary. How do we build something quickly and get it into market, but build it in a way that allows us to rapidly evolve our architecture to scale? We knew we would eventually need some kind of microservices architecture. This would ultimately allow us to scale the number of components that we had independently, and it would allow us to scale in the number of engineers productively working on our platform. And so we planned for this microservices future, and we built and shipped a monolith. But baked into this monolith's design was a pathway to scale. It was completely stateless, which allowed us to scale horizontally using elastic load balancing and auto-scaling. And it was carefully modeled around the key entities we had identified. And we implemented this model with some simple rules to make it decomposable in the future. Each entity was encapsulated by a service interface. And our service interfaces strived for consistency around a really simple set of CRUD verbs. All the business orchestration has to happen above this service abstraction. These rules allowed us to tease apart this monolith relatively easily when the need for scale came. Our service interfaces became RPC stubs, and one execution unit evolved to one per service. Now, our initial architecture was backed by a single RDS MySQL database. But in designing our schema, we similarly tried to anticipate scale. We maintained strict isolation of entity relations. If you needed to perform some business orchestration that involved more than one entity, you must compose that using the CRUD operations on the services. As tempting as it was, cross-domain joining at the persistence layer was strictly forbidden. This meant that our one MySQL instance was easily decomposed into multiple MySQL instances as the need for scale came. And each MySQL instance, we could add more scale. We can scale out through read replicas, and we can scale up through instance sizing. And then finally, as our exponential growth exploded, many of our services migrated over to DynamoDB, which continues to give us global scale. Now, I would love to tell you that this process of evolving our persistence was always smooth. It was not. The thing about exponential growth is that it can be hard for humans, even engineers, to grasp. And we felt this acutely in our media service. The exploding popularity of Canva meant that our media service MySQL suddenly got really, really big on us. We knew we had to get over to DynamoDB, and to buy time to engineer a seamless transition, we raced to put an abstraction layer over our persistence, and at the same time, we milked every last bit of life out of MySQL, which by that stage was groaning under the weight of tables hundreds of millions of rows in size and growing by tens of millions of rows every day and hitting new and exciting RDS limits on a regular basis. And the joy of building Canva in Sydney, Australia, is that the US traffic peak is just after 1 a.m. Sydney time. So we'd often discover these limits in the haze of a middle-of-the-night on-call alert. Now, stretching the capacity of MySQL involved lots of database dark arts. We first removed all foreign keys because they prevent zero downtime schema migrations. Then we started denormalizing a bunch of the schema because at that size, even joins become prohibitively expensive. And finally, we started consolidating data into JSON blobs in text columns so that we could lift the schema management up into the application layer. By the time we were ready to switch over to DynamoDB, we had morphed MySQL into a dodgy KV store. And the middle of the night wake-up calls were getting pretty boring. But get there we did, and today our DynamoDB-backed media service manages 93 billion items, and it's growing at around 90 million items per day. And we get really impressive performance and reliability. Fundamental to evolving for scale at Canva is investing carefully in the abstractions we provide within our architecture. We strive to make them powerful, consistent, and composable. We've now carried that focus and care forward in developing a powerful API that lets anyone build functionality on top of Canva. We offer the Apps SDK, which lets you build embedded functionality in Canva, and the Connect API, which lets you embed Canva functionality in your platforms. Today, thousands of developers in more than 120 countries are building on Canva and contributing to a thriving marketplace of over 300 apps and counting. And these apps have been used over 1 billion times by our users. On the screen is one of my favorites, the Crikey 3D animation app. During its first month on Canva, Crikey saw a 10% conversion rate among Canva users who tried it. Thank you for letting me share a little snippet of Canva's engineering journey. Our founder, Mel, wants to put Canva in the hands of all 8.2 billion people on the planet. She loves to say, we're only 1% of the way there. Now, I don't want to quibble with Mel, but at 220 million monthly actives, my math tells me we're actually closer to 2.72% of the way there. I can't wait to see what the next 10 years and beyond will bring, and I really hope that you will join us on that journey. Thank you.
Thank you, Brandon. Isn't that an amazing story? But if you look at behind the scenes, the evolution of it is something that many of us go through. They have an amazing, relatively simple app, simple application, but behind the scenes it's becoming more and more complex over time to provide their customers with additional functionality. And I think it's something we all go through. Evolution is fundamental. Even Darwin had already figured out that the only way to a successful complex organism was through numerous, successive, slight modifications. And Heraclitus, way before 500 years BC, already had this famous statement that change is constant. Now, the idea that we can stop our world and nothing ever changes again is just an illusion. The real world always changes. And our digital subjects, digital systems, are subject to that as well. Heraclitus also had this famous quote saying that the world is a context flux, you never step in the same river twice. And changes occur constantly in our environment, in our requirements and our implementation. And actually that's not some new discussion or something like that. In the 60s already, Lehman laid out a whole series of laws that have to do with the laws of software evolution. Now, it's nothing to do with distributed systems or cloud or the way that we build things now, because he was thinking about mainframes, but it is the laws of software. Software becomes irrelevant if we don't evolve it. If there's no new functionality, customers will perceive our systems as declining quality. And as such, now, we are in our digital systems continuously confronted with the fact that we need to evolve. And so, to help us with that, I kind of put 6 lessons together that I think are sort of the fundamental lessons that we've learned at Amazon. And I hope that they will help you as well to think, how to manage your environment to get complexity out of control. But remember, simplicity requires discipline. From day one, when you start making your designs, you need to start to think about that maybe it's simple on day one, but it will become more complex over time. So lesson number 1 is actually, as always, I think the most important one. Make evolvability a requirement. You need to know that your systems will grow over time and that you may need to revisit the architectural choices that you've made. I think if we did one thing really, really well with Amazon S3 on day 1 was that we knew that we were not running the same architecture a year from there or 2 years from now. And often, I think in the early days, I thought that whenever you change an order of magnitude in scale, you'll need to revisit your architecture. Constructing architectures that can be evolved in a controllable way is crucial if you want to survive complexity. And I define evolvability as a software system's ability to easily accommodate future changes. Now, this differs from maintainability. Evolvability is long-term, coarse-grained, radical, functional, or structural enhancements, where maintainability is fine-grained, short-term, local changes. Often they're corrective, or they're adaptive, or preventive, or maybe you just want to make your system more perfect. But those are maintaining. That's maintainability, not evolvability. Evolvability is long-term, having a strategy how to deal with complexity over time. I think that when you build evolvable systems, there are a number of sort of hardcore lessons that we've learned. Make sure you can build focused components. That means you have to model on business concepts, you hide the internal details, you put fine-grained interfaces over it. And then you build smart endpoints, use decentralization and independent deployability to allow these pieces to evolve separately. High evolvability, high observability, support for multiple paradigms. We get the insight and we are flexible in how we actually implement the different pieces of our systems. Now, I often like to talk about Amazon S3, and even in the video up front, S3 played an important role. Because I think it is such an amazing example of how a simple service grows more complex over time under the covers, but keep it simple for our customers. If you look at S3, isn't it amazing? This is, what is it now, 18 years ago? That, we have used cloud storage with just a simple API. It was focused originally on durability, availability, cost effectiveness, but the original principles founded a foundation for all these innovations that were happening after that. That is somehow driven by customers and often requiring significant rewrites. High availability and durability, we maintained that while the system was evolving. That's a great analogy someone once told me. The evolution of S3 is something like we started off with a single-engine Cessna, moved over to the 737, then eventually ended up with a whole fleet of 380s, moving customers along the way without them noticing it and refueling in midair. And that's how it felt with building S3. And you see that every year we added new functionality without any impact on the functionality we were delivering for our customers. That strong consistency means that we were no longer compromising on our core attributes. Modularity allowed us to experiment with languages like Rust. Now, from the start, we had a very clear strategy for complexity, a microservices architecture. And if you look at the evolution of the microservices underneath there, it is quite spectacular. We started off with 6 microservices on day 1. Now we're well over 300 of them. And they've grown over time. And we all use S3 without noticing that this complexity grew significantly under the covers. Now, it's not only, by the way, software is easy to evolve because we have total control over it. One of the things that actually we really had to make changes into was sort of the hardware infrastructure. If you think about network devices, in general, all the functionality is built into ASICs. And every change you need to make, you often need to completely swap out your networking device. That was definitely in 2006 the sort of common knowledge. But our customers were reconfiguring the network the whole time, and our network boxes were actually really not built for that. So we needed to create a foundation on which we could evolve. Because we knew that whatever networking capabilities we're giving you in 2006 will be radically different in 2010, and definitely in 2020. So we created a a foundation for innovation. We call Blackfoot. This was a device, basically a whole bunch of line cards originally, Linux kernel on the side, but it allowed us to evolve our networking over time. Yeah, and well, maybe the earliest device will give us 10 gigabits a second line speed. Now we're in the hundreds and hundreds of gigabits a second for you, while evolving these devices and while evolving the security of our network over time as well. So create a foundation for evolution. Same as for the hosts. At some moment, we realized that the way that we were building our hosts were actually not a good platform for evolution. Separating a number of functionalities into a separate box with cards, like Nitro, was crucial for us to be able to evolve our host systems. In those days, in the earlier days, processors were getting so fast that root I/O virtualization of the virtual machines were getting in the way. So moving networking out of the box, for example, allowed us to continue to do virtualization while getting access to full line speeds. And we could actually do encryption at line speed. And we could build PCIe interfaces for access to EBS. Again, evolvability is a conscious decision. You have to create an environment in which you can evolve. You have to make evolvability a requirement, because it's a precondition for managing complexity. Now, if you think about how complexity grows over time, I like this analogy, again one by Colm. If you put a frog in a pot of boiling water, it will know something is wrong and immediately jump out. However, if you put the frog in cold water and then slowly starts to heat up, it remains comfortable. Small warning signs are there, but they're being ignored. It just adjusts to the nicely increasing warmth. By the time the frog realizes that there's danger, it is too late to escape. By the way, no frogs were harmed in this analogy. The lesson there is, do not ignore the warning signs. Small changes seem manageable, easy to absorb at first. But if you ignore the warning signs, systems become more complex and more harder to manage and to understand. To be able to do that, to really manage that, you have to break complexity into pieces. A good example there is Amazon CloudWatch. Now, we all use CloudWatch. But today, this is a massive service. Really, hundreds and hundreds of trillions of metrics observations a day, almost half an exabyte of logs being ingested every day. This is a crucial, fundamental service in AWS. Didn't start off like that, though. No, the early days, CloudWatch was a very simple service. This was how it looked like when we just launched it. And it was just a service for storing and receiving metric data. Just a couple of back-end servers, a small team of engineers who understood every part of the system. But over time, the system starts to grow. And the front end was actually the place where everybody was implementing the new functionality. And this grew over time. And they became more complex, and actually a sort of an anti-pattern arrived, which I call a mega service. A mega service is an anti-pattern in that you get complexity that you need to start breaking up. Now, the front end only handles only the core functions, and the complexity of the whole system is moved into individual pieces. The principles we use over and over again: you need to disaggregate your system. You need to build components that have high cohesion, but are loosely coupled to others, and have well-defined APIs. This is how CloudWatch looks these days. A very simple front-end service. Actually, probably the only code that's left from the early days is something about handling the original requests. But for the rest, everything has been rewritten and rewritten over time, and new functionality gets handled all the time as well. And there's many different reasons why you have to change your system. It's not only adding new features. But for example, one complexity issue that we have is around engineering here. Many of our high-volume data stores in CloudWatch have been written in C programming language. It is very hard to hire C programmers that can actually operate at this particular level. So, we're actually starting then to think about, how can you have disaggregated everything, these small components that are individual. It doesn't really matter which programming language you pick. So in this particular case, we started to use Rust to start implementing these high-volume interfaces. And again, it's one of these things that you can do if you decompose your systems into smaller building blocks. They can evolve over time, not only with respect to functionality, but also, for example, with respect to the libraries and the programming languages that you use. Now, the question I always get is, if you think about breaking into pieces, how big should such a service be? In general, you don't have that much choice about it. Things are often from the outside that determines it. Yeah? How many teams do you have? How much success do you have? Customer demand. And in CloudWatch, we have a lot of microservices, and the size of each of them is actually dependent on the path, and it's organic. So I don't have really good advice for you to say, and this is how big it should be. Now, you have two options when you get new functionality. Yeah? You either extend existing ones or create a new microservice. Extending is often faster. It reuses code, and you risk sort of this mega service anti-pattern. You create something new, it keeps service manageable, but it requires more effort up front. So the warning signs are, a microservice turns too large for an engineer's mental model. If you can't keep it in your head, your service in general is getting too big. Now, someone who grapples with these challenges on a daily basis is Andy Warfield. So please join me in welcoming Andy, who will share how Amazon S3 organizes itself to handle this sort of complexity. Andy.
Hi, everyone. I'm Andy. I'm an engineer on the S3 team, and I'm going to talk to you a little bit today about organizations and complexity, and how we structure our teams and organizations to deal with complexity. Now, as Werner said, S3 has been around for 18 years, and I find this remarkable. It's kind of the coolest thing that I've ever worked on in my career. The idea that a single distributed system and a single team has actually run continuously for 18 years. And so I'd like to make a couple of observations about some things that I think are interesting and successful about how the organization works. But I got to start with a disclaimer. Because I would hate for the team to feel like I got up here today and told you that we had figured this out, that we'd solved the problem of organizational complexity. I think that we actually have it. I think we still have a lot to learn, and we're learning every day. The system continues to evolve, the team continues to get bigger, but when we are at our best, I think we get a couple of things right, and I think they're worth sharing. So before I tell you about the two things that I think we get right, I have a question for you. Does anyone know what this is? Has anyone ever seen one of these? There's no wheels at the front. This is a sled from a tractor pull. When I was a kid, I grew up in Ottawa, Canada. We had family that lived about an hour from town, and at the end of the summer, every year, we would drive out and go to a country fair in Shawville, Quebec. And the fair had, all the stuff that's awesome about country fairs. Contests for the largest vegetables, a midway, and of course, a tractor pull. And so the tractor pull involved farmers bringing their tractors out. They'd attach it to this sled, and there'd be a track. It was especially awesome if it was rainy, because it'd be muddy. And through a combination of the power of the tractor and the skill of the driver, they'd pull the sled as far as they could down the track. But as the sled pulled, the bucket on top that was full of weight would make the sled heavier and heavier. So this is a weird diagram, but this is basically how I think about software development. There's this incredible commonality between tractor pulling and developing large distributed systems. The commonality is that as you pull, it gets heavier and heavier. On the first day, staring at that empty buffer, it's the most awesome time in terms of the openness and possibility and the lack of burden. But as you pull, it gets heavier and heavier and heavier. You accumulate complexity. And you can go a certain distance through sheer power and force of will, but ultimately you have to acknowledge the weight of the sled. And so I think, as a sort of general observation, we need to acknowledge that our organizations are at least as complex as the software we build, and we need to give them the same attention. So the first observation that I'd like to make, that I think the S3 team does a pretty good job of, is that successful teams tend to be at least a little bit scared all of the time that they're getting it wrong. They're always looking for the things that aren't quite right. And when things are going really well, that's when you're kind of the most scared, that you've missed something. And so being a little bit scared and asking questions and trying to improve is a thing that the S3 team, I think, does a good job of. I'll give you one example. About 6 years ago, we were going through this period where we were growing a lot. We were bringing on a lot of new engineers to the team. And S3 cannot miss ever on durability. Durability is so central to the engineering team and the way that we approach things. But we were concerned that we had to maintain this focus and this sort of investment in durability as we brought on a whole bunch of new folks that were great engineers but hadn't worked in this kind of environment before. And so one of the other PEs and I, Seth Markle, sat down and talked a lot about how we were going to do this. And we decided to build a program where we borrowed an idea from security engineering, the idea of a threat model, where you write down your security threats and you assess whether the model matches your defenses. We came up with the idea of a durability threat model and built a structure where when the teams were going to make changes to S3, they wrote down the durability risks that they could anticipate and what they were doing to make up for them, to counter them. And then we could take a smaller number of engineers that had been on the team for a long time, that had tons of operational and engineering experience with durability, and we got them to act as durability reviewers. And we would sit down and have these awesome conversations around the durability threat model where we'd try and poke holes, and we'd find stuff, and we would improve, but we would also teach as a consequence of that thing. And so it's one example. There's hundreds, probably, of examples of mechanisms that we've done to sort of scale the team, but the bottom line is that we are encouraging questioning, right? Consciously challenging the status quo. And to borrow a quote from Grace Hopper, right? When we start to see things like people saying, we do this way because we've always done it this way, it's an example of a warning sign that maybe you should be asking more questions and maybe you should be a little bit more scared. So that's one. The second observation that I'd like to call out is this idea of ownership. And I think ownership is something that is absolutely fascinating about S3, but AWS engineering all up, right? The way that Amazon builds. And ownership is really hard to describe. So I'm going to try and do it to you with a quick exercise. I'd like you to think of a time in your career or in your life where you've worked on something that you really, really loved, that you cared about. And in that instance of working on that thing, I'd like you to think about how hard you worked, how invested you were in quality, and how much you really were excited to deliver it. And now I'd like you to flip and think about a time where you were working on something because you were told to do it. You were working on something that you didn't necessarily feel that you understood the benefit of or the outcome for, but you had to do it because you were told to. And I'd like you to think about how much you worked on that one and how eager you were to land it and how the quality of that one worked out. The difference between these two things, to me, is kind of the property of ownership. A team that owns what they're working on is in the first category. And when I look at the most effective leaders that I work with, they're incredible at driving ownership. And I see them do two things. The first one is they build a sense of agency within the teams that they work with. Agency means letting the teams feel that they've got the breadth and the support to really deliver. And so the first step in building agency is to not tell the team what or how to do, right? It's to bring a problem to the team, to explain the importance, to get the team involved, and to ultimately trust them and to give them ownership of what they're building. And in giving it, we're actually letting them own the idea and letting them celebrate the win because it's theirs. So that's the first thing that I've seen leaders do that's super, super effective. When you have a team that has agency, the second thing that really effective leaders that I've worked with, especially in S3, do is they drive urgency. Because even the best teams will find ways to slow down. They'll find surprises, they'll find things that they're worried about shipping, and you're always, always having to make decisions and compromises as you ship. And so moving fast as a leader means establishing ownership, stepping back, letting the team run, but keeping your foot on the gas and making sure that you're checking in and helping problem solve and helping the team feel that there is a need to deliver, but they're supported to deliver. And so really, ownership is this combination of agency and urgency. And that's it. The two things that I discussed were that you should be a little bit scared and that you should push ownership all the way down to the level of 2 pizza teams and let those teams really own what they deliver, focus on letting them love their work, but drive them to deliver with support. Thank you very much.
Thank you, Andy. Amazing stories in how AWS evolved, not only from an architectural point of view, but also from an organizational point of view. Yeah? And we have many of these stories. And Andy, as being one of our distinguished engineers, really focused as well. And I hope that over time we have so many of these distinguished engineers that have great stories to tell to you. I hope they're able to sort of bring them in front of you over time. Now, lesson number 4 is we've just broken things down into smaller building blocks. Yeah, and we've aligned our organization with how we want our architecture to look like. But then we get to the point that we not only actually need to sort of build them, we also need to run it. How can we make sure that the operational complexity also maintains handled? In Amazon, we do this by organizing these applications into what we call cells, cell-based architectures. Yeah? You've built your application. You know, you have some front end, you maybe have some containers in the middle, you have some data storage in the back end, and then you start to become more successful. Things start to grow. And any form of disturbance in the operations of that will affect all of your customers. Yeah? It will impact performance, or when a customer gets hot, or some failure somewhere will take down your overall service. All your customers will be impacted. And so managing this is actually highly complex in this architecture. So you need, again, to break things, to decompose them into smaller building blocks that each operate independently. The goal here really is to reduce the scope of impact, which is essential in a complex system. Cell-based architectures, you divide the system in isolated, independent cells. And you pick a deterministic algorithm, often a hash function, that maps customers to specific cells. These cells, they create order in a complex system. They isolate issues to specific units without impacting the other units. And so to be able to implement this, of course, you need some sort of simple router. And this router is very simple because the only thing it needs to do is forward requests to the right cells. By the way, a very cool algorithm to allocate customers to cells is called shuffle sharding. And there is a great article in the Builders Library on that, if you're interested. It is a unique way to maximize availability of the overall cells. Now, how your cells look like depends a bit on where you started off with. If you have a regional service, then your cells remain regional as well. They're just smaller building blocks. If you had a zonal service, you may end up with many more of these cells, but still decomposing them into smaller blocks such that complexity becomes manageable. Now, if you look at some of the different AWS services, how do they use cells? What is the sort of the ID that they're routing on? CloudFront does this on distribution ID. Route 53 does this on hosted zone ID. And the hyperplane, which is sort of the back end of EC2 and the load balancers and things like that, do it on customer ID, which is, by the way, a great default if you have it. Yeah? You also need to develop a little bit of a control plane next to it to be able to sort of manage the different cells. And as new customers get onboarded, you may create new cells, or you may split them over the existing cells. All of this is something you have control over. Now, just like with services, how big should a service be? The question is, how big should a cell be? Well, a cell should be so big that it can handle, the biggest workload that you can imagine. But then it also should be small enough so that you can actually test it with a full-scale workload. Yeah? And probably, the right answer is somewhere in the middle. Mostly because you want to benefit from economies of scale. Yeah? The bigger the service is, the higher the likelihood is how many more customers are impacted by an issue. Yeah? And the smaller you make them, the less impact of economies of scale you have. So it is, as always, a balancing act. But the one thing, when we add here, of course, additional complexity when we think about cell-based architectures, because now you have to manage this. This is something you have to do up front. But you have to remember that the time to build a system is often minuscule compared to the time that you're going to run the system. So investing in manageability up front is crucial. Just like you need to invest in security up front. And you need to invest in cost control up front. Yeah? Decomposing into cells is something that will help you over time maintaining reliability and security for your customers. There's a great article in the Well-Architected Framework Review that actually deals with all the different sort of ins and outs if you want to build a cell-based architecture. If you're interested, I urge you to read that one. So read it, organize it to cells, because in a complex system, you need to reduce the impact of any issues that you encounter. Another lesson that we've learned is that you need to remove uncertainty from your systems. Yeah, because uncertainty is very hard to handle. So you have to design your systems up front with reducing complexity in mind. Imagine you're tasked with designing a configuration system for something like Hyperplane. Yeah, where you have all the load balancers and customers are continuously reconfiguring their load balancers. Especially if you have millions and millions of customers, this happens all the time. Sort of a common approach would be to use an event-driven architecture. Yeah, sort of the configuration changes are being stored in the database. You then send out events, maybe a queue. You fire up a Lambda that then reconfigures the load balancers. But if this is continuously happening, it becomes rather unpredictable how much reconfiguration load these load balancers have to take. Yeah? Now, plot twist, this is not what we did. Yeah? Because the processing at the load balancers becomes totally unpredictable. What we did is a much simpler approach. Basically, we push all the changes, we keep them, we write them in a file, store them in S3, and the load balance is on a fixed loop. Every few seconds, pick up their new configuration from S3. And this file has a fixed set of entries. And they always process all the entries. As such, reconfiguration is completely predictable. It's very simple. Now, this is really using simplicity to build a system that is highly predictable. Now, this doesn't look like some magic architectural change, but simplicity will help you here to create predictable processing. It's a pattern we call constant work. Yeah? Consistently pulling a file from S3 avoids spikes, avoids backlogs, avoids bottlenecks. And it's also naturally self-healing because the availability of S3 is unparalleled. Now, let me give you an example of another service that makes use of constant work, which is Route 53 and the health checkers. So we have a whole fleet of health checkers that you have configured for yourself, whether a node is available or not. And so instead of doing pushes every time for every change that is happening, periodically the health checkers will just push out a complete configuration file to aggregators of all the nodes that they are responsible for. The aggregators merges all these requests and then pushes this into a bigger table and then pushes this to Route 53, which does nothing with it. Nothing happens on the arrival of that table every few seconds. Only when a DNS request arrives and it is being resolved to a set of IP addresses, you check this table whether hosts are available or not. Processing in this system is no longer driven by the events. It is highly predictable, and as such, the complexity goes out of the window, and it remains simple. But again, this is intentional. Simplicity requires discipline. Now, you have to design predictable systems, which mostly it's really to reduce the impact of uncertainty. Now, the last lesson in this row of how to manage complexity is to automate complexity. It is essential for managing complex large-scale systems. AWS uses automation for durability, for capacity. Actually building new regions is completely automated. There's hardly any humans involved at all. Or the examples I gave around networking. Customers continuously reconfigure their networking capabilities. And as such, we needed to completely automate that. Now the question is, what should you automate? Which is the wrong question. The right question is, what don't we automate? There's only those decisions where humans really need to be in the loop, need to be made explicit. Automation for everything else. If you consider what do we automate, it is much more like the standard behavior instead of humans in the loop. No, automation should be the standard, and the exception should be where we have humans in the loop. Manual input should only be required in those areas that truly require human high judgment. And actually, a common practice or a really practical approach there is that not have one human typing commands. Always let another human actually look over its shoulder to actually make sure that we as humans don't make mistakes. One area where we do a lot of automation, a lot of automatic processing is that in security. Now, of course, at AWS, everyone has a security job. We're all security engineers. Because security needs to be first and foremost in your mind if you want to protect your customers. And by designing with security from the outset, we embed security into our services as they are created, instead of sprinkling something over it afterwards. And so our security teams not only help us build secure services, they also build technology themselves. And for example, around automated threat intelligence. We have such a huge network over the world, and we have such an impact. You see such an impact of changes there. Literally trillions of DNS requests a day, and we easily identify well over 100,000 malicious domains on a daily basis. That is all through an automated process. It is a neural network that these requests are being pushed through, and then automatically we detect which ones are actually malicious. Then that information automatically flows into guard duty so they can protect our customers. This would be, if it would be by hand, it would be an enormous process, overwhelming. And automation here helps us sort through the ever-growing volume of data. And then we're able to feed this intelligence into guard duty. Now, another area, and it's definitely something that I've seen inside the security team, is something we are all focused on. Yeah? We all have support tickets. Well, at least we have, and I assume most of you have as well. And most of these support tickets are actually intended to be processed by humans. But I believe that sort of newer technologies will allow us to actually do a lot of automated processing of these support tickets. You can implement an agentic workflow to automate some of this process in a way to reduce the complexity of resolving tickets. An agentic workflow looks like something like this. It is a system that operates independently to accomplish tasks. The agents are specialized for very well-defined, narrow use cases. They're capable of sort of planning, iterating, using tools, and sort of automate this. This is sort of an example of how we use an agentic ticket triage system. Basically, the goal of the agent is to efficiently resolve support tickets. And the process then becomes read the ticket, use the tools, iterate, it categorizes, it prioritizes the tickets based on analysis, and it determines the action. It could be to resolve automatically, or it could be to escalate for human review. Now, how many times haven't you actually opened up a ticket and looked at all the different information pieces that you needed to look at? Database here, information about the customer over there. We should be able to actually present you with a complete picture of the world if you as a human needs to use your high judgment to resolve this ticket. Now, if you're interested in this agentic workflow, Claire Legueris has a very interesting GitHub repository that allows you to give you a really good base for doing this sort of serverless prompt chaining. And there's also a great self-learning course that is about creating serverless and agentic workflows with Bedrock. It allows you to focus on automatic resolving issues. That's really great, because many of these tasks, especially resolving tickets, is kind of boring. Yeah? Some of this hard work that you absolutely just need to do, but you prefer not to. And as such, the quicker you can use to actually use your high judgment to create this is perfect. So, automate complexity. Yeah? Automate everything that doesn't require high judgment. So these were sort of my 20 years at Amazon in thinking about sort of the many lessons, but definitely lessons in complexity. And these are the most important ones. I'm pretty sure if you talk to distinguished engineers at Amazon, you'll get many more lessons, because all of us have scars around this. And we've learned this the hard way. But simplicity allows us to scale our systems to become more complex over time in a safe manner. So, make evolvability a requirement, break complexity into pieces, align your organizations to your architecture, organize into cells, design predictable systems, and automate complexity. And so I shared my lessons here, but I'm pretty sure you have your lessons here as well. And I, as always, actually really would like to compliment the heroes in the audience. Because the heroes are a group of people that continuously share their lessons with the rest of the world and build communities. Heroes, can you please stand up? Where are you? Come on. Over there. There are now 257 heroes out of 53 different countries. They're the feet on the ground that help everybody else be successful on our platform. Please listen to them, engage with them, because they have lessons to tell you that are valuable in building your own systems. Now, they're sharing their lessons, but a company who uses technology to do a lot of good, specifically addressing food waste in this world, is a company called Too Good To Go. I'd like to welcome their VP of Engineering, Robert Christiansen, to talk about their evolution. Robert.
Hey everyone, a quick show of hands. Put your hand up
if you've ever thrown good food in the trash. Come on. Well, you're not alone. Did you know that 40% of all food produced around the world is wasted? That is like going to your favorite pizza place, taking 4 slices out of the box, dropping it on the floor, walking away, leaving them there to rot. Food waste accounts for 10% of all greenhouse gases emissions worldwide. 4 times more than the entire aviation industry. Of all of the environmental challenges we face together, food waste is by far the dumbest. Too Good To Go was founded in 2015 in Copenhagen by a group of young entrepreneurs. And they had a vision, finding a solution for the massive amounts of food wasted by buffet restaurants. They knew people prefer to buy the food at a discount rather than seeing it tossed out. That simple idea grew into the world's largest marketplace for surplus food. In the first few weeks after launch, hundreds of businesses uploaded their surplus food to the Marketplace app, and thousands of users collected their surprise bag of unsold surplus food. A win-win for the planet and their pocket. Our founders were entrepreneurs that started out with a strong conviction and a smart idea. But one thing, they were clearly not developers. The technical foundations of the app was not the most resilient back in the day. And that created problems as we grew. And we grew fast. In 2018, after we had our first 1 million registered users, the platform started to struggle. Our application was a classic PHP application with a single MySQL instance. Our systems was overloaded daily. We did not want to build a space shuttle. All we wanted to do was to scale and keep things simple for our 10 engineers. So what did we do? We started out with the easy options available to us. We could buy ourselves a lot of runway by using Amazon Aurora's built-in support for up to 15 reader nodes. We identified our read-only use cases and used separate connection pools in those instances. Then, we chose to rewrite the application into a Spring application, one endpoint at a time. That way, we could take advantage of better resource management, connection pooling, cache, message queue integration, and processing. We did not have to build a spaceship. We could simply take components off the shelf. We only needed to customize a little, mainly to achieve scalable high-performance endpoints, specifically those that could be treated as eventually consistent with lots of traffic. At 1 million users, we have almost been overwhelmed. But with these small improvements, we made it to 10 million registered users just 4 full years after launching. Our user growth continued to accelerate, and at the same time, the business wanted new features. And that brought us new challenges. When developers were facing the same scaling requirements, we wanted them to take from a central toolbox. Remember, we wanted to keep things simple. We went with a focused architecture where language and framework were fixed. Common patterns like transactional handling, caching, messaging, security, and background processes were a given requirement and the same for all our services. Fixing the language and architecture in these instances lowered the technical complexity. This made the life of our engineers a lot easier. At this point, we are serving most of our traffic from eventually consistent sources, caches, and Amazon OpenSearch, protecting our transactional databases from large amounts of read traffic. And it allowed us to grow. By 2020, we had 24 million registered users across 16 markets. But food is wasted everywhere on this planet. More impact for us meant more growth. After Europe, we expanded to our first new continent, North America, in 2020, different partners, different habits, different time zones. We wanted to be local from the first day, low latency, and a great customer experience. But we didn't want to build a new app or infrastructure in the US. Remember? Keep it simple. Being on AWS made it possible. They have regions around the globe, so we could process locally in North America. But what does it mean to be in multiple regions? Do we duplicate everything? We wanted to expand on what we have, keeping it simple, but that did not mean it was easy. We went with an approach that fixes transactions for customers or partners in their home region, and we spread out the data we use to serve most of our read traffic. It required us to plug in Amazon SNS topics and Amazon SQS queues to spread out updates to foreign regions whenever data was updated locally, creating an additional patterns our developers could use. It worked very well, but it took a lot of work. And as you might start to imagine how it looks when the number of regions grow. With this, we continued our expansion across North America, launching in Phoenix, Detroit, and Cleveland this year, just to name a few. We were able to use the same blueprint to launch in another continent, Australia, this time with minimal effort. And today, we're a thriving community with more than 100 million registered users and 175,000 active business partners. So far, Too Good To Go has helped save over 400 million meals from going to waste. And we want to make an even greater impact. This year, we launched a new product, the Too Good To Go parcel. You can get groceries close to the end of their shelf life, avoiding food at the manufacturer level. Growth is what you want as a startup. But from a tech perspective, it can make for a rocky ride. One thing is certain, saving food with Too Good To Go must remain simple. Because right now, we are saving 4 meals per second, but every second, 80,000 go to waste. There's a huge opportunity ahead. The health of our planet depends on it. So, let me leave you with a question. How will you save more food from going to waste? Thank you.
So tell me, Dr. Werner, what's next? What innovations are customers looking for now?
Well, we just finished working on an interesting database right now, which is beautiful in its simplicity.
Multi-region, multi-active, distributed but enables synchronous data replication with zero data loss. Simplex.
3 words: pizza, friend, chaz.
Idiot.
Maybe it's just easier if I explain it.
Okay, great. I love hearing from customers like Robert and Too Good To Go. He really articulated the sort of complexity that they faced growing, expanding, and dealing with data across multiple regions. As always, I think that we look at these kind of companies and the challenges that they face in evolving their architecture, and then we look at what kind of technology should we be building to make this much easier for you. Now, if you think about sort of the burden of complexity, we always sort of want to make sure that we can take on more and more of the burden of complexity that you're facing by actually building simple systems ourselves. The goal is to make the customer experience dealing with databases, for example, as simple as possible. But if you look at the complexity burden over time, when we started off first AWS, you were probably running your own databases. Or, quite often, customers still do lift and shift to architectures that were on-premise into the cloud, and they will be there running their own databases on EC2 and running read replicas and other AZs and things like that. The complexity burden was really on our customers. But the first step we did is actually managing those databases for you with RDS. Yeah, it significantly reduced the operational complexity. Yeah? No more patching, upgrades, backups, read scaling, and it definitely handles the complexity of maintaining high availability, for example, and it simplified recovery processes. But we were still running standard databases inside RDS. And to be honest, that wasn't a really great foundation for doing innovation in database work. Because most databases are built as one big monolith that is very hard to make changes into. So the first thing we did was actually start building Aurora by decoupling compute from storage. Suddenly the log became the database, and that allowed us to move much faster. Yeah, you separate the storage from the engine so you could scale more seamlessly without having to worry about your storage. Yeah, and then we're able to do innovations in this world like Aurora Serverless and Aurora Limitless. And they took this even to a step further. Yeah? Basically, on-demand scaling, removing capacity requirements up front, and the ability now also to scale down to 0. And on Tuesday, Matt announced Amazon Aurora DSQL, sort of the next era of Aurora. Yeah? DSQL enables applications that can serve customers worldwide, like something that Too Good To Go had to deal with. The question is, would their architecture look differently if it would have had DSQL available to them? Yeah? And it allows for failover without disruption, and you can do some sort of optimized data placement, both for performance as well as for compliance. Yeah? It provides you with the tools to build a globally distributed applications with the resilience required to serve hundreds of millions of customers. Yeah? Now, I'm not going to go into all the features and functionalities and whatever of DSQL, but I want to use DSQL as an example of how we apply the lessons that I talked to you about earlier on to manage complexity upfront in the design of DSQL to make sure it is the right foundation for evolution over time. It is a hierarchy of independent components that are each distributed and resilient. And we use the same principles that we've talked about before. System disaggregation, decoupling into smaller building blocks, each of those building blocks having high cohesion, functioning on one particular task. Low coupling, so that you can individually scale those components, and have very well-defined APIs between them, because that's how they communicate. This gives you very fine-grained control over your system, and it allows you indeed to individually scale the different components based on their needs. And it also allows you to tailor the security for each of those components dependent on the specific requirements of them. Now, if you look at sort of the high-level building blocks in DSQL, there's a front end, there's a query processor, which is handling actually most of sort of the SQL processing. There's an adjudicator that coordinates with respect to whether transactions can actually be committed. There's a journal that requires short-term storage. There's a crossbar that actually sort of merges these things to its long-term storage. Each of these components scale in different ways. The query processor scales with the number of sessions. The adjudicator scales with the number of transactions. The journal scales with the amount of throughput that you can actually have in one of these storage systems. And the crossbar, again, scales with the number of journals that you have, as well as the size of the database, which goes to the storage as well. So each of those components scale individually. If you would have put them together into one big monolith, as the traditional databases are, you would have to scale everything at the largest scale of one of these components. Massively overscaling and becoming extremely inefficient and much harder to manage. Because now we have components that we can also evolve independently. So let's take a look how some of these components work together. Let's start off with doing a simple read transaction. Yeah? Imagine a user that is looking to order a pizza here in a local restaurant here in Vegas. Yeah? You have all written these SQL queries. Yeah? Select from restaurants where the rating is more than 4. So what happens behind the scenes at this point? Your application makes a connection to the front end, which actually allocates a query processor. Query processor is a very small, independent component that we allocate for each of these sessions. Yeah? The SQL arrives there. We get a timestamp to put at the beginning of the transaction. It reads the local clock. And it then sends out these requests. Oh, no. First, it does something else. It actually consults something called the shard map. Yeah, because in storage, the storage is actually sharded according to, for example, database keys. So it needs to go to the shard map to understand which of the storage engines actually holds this data. And given that this is a read, it doesn't need to go through the transaction path. It goes directly to storage to actually retrieve the data. Now, the storage in DSQL is not your typical database storage. Typical database storage would basically be that you would retrieve a page, and in that page would actually contain the data. The storage in DSQL is database aware. Meaning it can do, for example, do something like filtering. That means that if I go to the storage engine, ask for this particular row, I only get that row back, or that set of rows, not actually sort of the complete page that may hold all of this data, and that I then need to lock. And that's one of the biggest sort of bottlenecks in traditional databases, so the way that they interact with storage. So these results are merged and they return to the user. So what happens next? At this point, the user figures out that Alexei wants to buy a pizza. And this is what we call an interactive transaction. And if you're a SQL developer, you're really familiar with interactive transactions. You start a transaction, you get some data, you do some work in the client, you make some decisions, you write some more SQL, you go back to the customer, and eventually you will actually sort of do a commit. And this is very different type of transaction from what you would have, for example, in DynamoDB, where you need to do all your work in one shot. So the query will look like something like this. It will become a bit longer. You would select a restaurant, you would choose an item from the menu, you then place an order, and what you'll do is you'll hit commit. Then the SQL as a whole package is being sent to the query processor that you've been assigned to you, and they actually merge it all together. And in DSQL, the query processor functions as a holding tank. It uses snapshot isolation, so it can do actually reads and writes on the data that it has in local memory. And it waits for commit before sending the full transaction to the adjudicators. The adjudicators are also, so basically what happens, all the sort of simple SQL statements are handled within one region where the query processors sit. And the only cross-region interaction happens when you actually are running a commit. If there are adjudicators that are running in a different region, you may need to evolve them. And this means that reads and writes and updates are just as fast as that they would be in a single region database. Now, the query processor is a very unique beast in that sense. And so a processor actually runs inside a small firecracker VM. And it's placed on the query processor host, which is bare metal, and we can literally run thousands and thousands of these query processors inside these micro VMs on a bare metal host. If the connection between the client and the customer, between the customer and the query processor actually goes dormant for a while because the customer isn't making a decision and as such you haven't seen a commit yet, we can actually sort of suspend this micro VM. And if then the customer resumes his action, we can actually restore the snapshot of the micro VM, and we can do that within a few milliseconds. So we can really optimize for long-running transactions. As I said earlier, in the query processor, we use snapshot isolation. which means that each transaction operates on a consistent snapshot of the database as it existed at the start of the transaction. And this allows reads to progress without blocking writes and vice versa. The transaction begins, proceeds through the SQL execution phase, where reads see this consistent snapshot. And when a write operation occurs, like an insert or an update, they may not immediately be applied to the storage. Instead, we spool these writes locally, creating a sort of a private workspace on the transaction. And this allows for example, read or writes capability, where subsequent reads within the same transaction see all pending changes. Now, the next, the transaction actually, both the write set as well as a complete post image, meaning that the view of the rows in the database after all these updates have been applied. So the write set, as well as that the image is being sent to adjudicators, plus time. We'll get there to that. The adjudicators then sit in the write path of the SQL, and they decide whether transactions can be committed or not. The job of the adjudicator is to detect and resolve conflicts between transactions and ensure that writes are consistent. But to do this, the query processor created a payload to send to the adjudicator, containing all the information it needs to make a decision. A payload contains a write set, all the items modified by the transaction, and a post images set, basically copies of all the table rows that are applied to the effects of the transaction. Now, the payload also contains the transaction start time, T-start, which is a crucial element in committing or aborting the transaction. Now, look at two concurrent transactions. Both are sent to the adjudicators, and they're roughly going at the same time, although transaction A has sent a commit slightly before transaction B. So what happens in this case? The adjudicators compare the payloads from the query processor, examining the transaction start time and the write set. They're looking for any writes after T-start proposed for table rows indexed by overlapping or matching keys. If they see that both transactions are trying to update the row identified by key 3. So they can't both change the row at the same time, since transaction A can commit, transaction B must abort. Now, if the write sets from the transactions do not intersect with each other, the adjudicator allows the commit to proceed. In this case, transactions are allowed to proceed and are assigned a commit timestamp, T-commit. Now, remember I told you earlier that in traditional databases, durability happens in the storage layer. Transactions are considered committed once they are durably written to a storage layer. And they are then expected to do all sorts of things, like recovery committed transactions after a failure, and they need to be keeping the in-memory and the storage sort of in sync to be able to, when you recover things, it's just very hard work. And we decided to make this a lot more simpler. In SQL, the journal is responsible for short-term durability. Transactions are considered to be committed once they've been written to a journal. And the journal can scale horizontally. And actually, they scale based on the throughput capabilities that each of these storage engines can have. But what we see there is then a total ordered stream of committed transactions in the journal. And this ordering is crucial for maintaining consistency across the system. We then actually have the crossbar that starts pulling the transactions of the journal and actually move those into the storage engine. So here we see, here's the adjudicators, goes to the journal. At that moment, we can send an acknowledgement back to the customer that the transaction has completed. As you can see, each of the components in this system operates independently. This is absolutely a great example of an architecture that follows the principles of managing complexity. Now, there was something in here that I kind of glazed over. Remember, there's these two things, T-start and T-commit. And it's an amazing example of really doing this complexity, but actually being really simple in how we do coordination with different components. Yeah? T-start and T-commit have read the local clock. But in a distributed system, that is almost impossible. You can't use a clock in distributed systems. Yeah? And remember, the concept of time is fundamental in our lives. Yeah? You all knew that I started at 8:30, and you're all looking at your watch now, when is he going to finish? Yeah? And so time is fundamental. Almost all of us carry time on our wrists. Yeah? And for us, sort of more or less, the accurate time is fine. Right? The approximations is fine. And if we would want to use time in our distributed systems, that was always considered to be impossible. And we've seen incredible, amazing algorithms being developed over time to create consistency, to do leader election, to do two-phase commit, all these kind of things that we needed to do because we couldn't use time. And there's a very famous paper by Leslie Lamport, end of the 70s actually, a very famous paper. He got the Turing Award for work in and around this. Time, clocks, and the ordering of events in a distributed system. Which basically says we cannot use time. And we actually have all these other kind of capabilities that we need to think about because we cannot use time. And if you look at all these different algorithms, distributed clocks, vector clocks, all these mechanisms that have been invented over time because we couldn't use time. A few years later, very interesting, in '91, Barbara Liskov, another Turing Award winner, actually wrote this paper on the practical uses of synchronized clocks. And it's amazing because he started describing all these algorithms that you could do, that you could build much more simpler if you would just have access to clocks, to time. Yeah. She also wrote in that paper, so only recently these distributed clocks, these synchronized clocks, have become in available systems. Well, most recently meant 30 years later. Yeah? 30 years later, we finally have high accuracy synchronized clocks. And that allows us to build our systems, our complex algorithms, in a much more simpler fashion. Now, we have a complete different infrastructure, a third backbone inside our data centers that is dedicated to only one thing, to serve you accurate, synchronized time. Yeah? And what we do, it actually comes from the satellite, we synchronize that, bring that over this complete separate backbone to a card that sits in Nitro, and where you, making use of the Amazon time servers, can get an accurate time. Yeah? And this clock-like accuracy is in the order of microseconds. Now, last year, Peter, already in his keynote, talked about how we improved this to microsecond level clocks and how this is available on each Amazon EC2 instance. This is sort of a graphic of how this looks like. Yeah? And so satellites reach the atomic clock, and then on this complete third level backbone, we use FPGA hardware and specialized Nitro cards, eliminating drivers and network buffers and things that always burdened NTP as the network time protocol, where you could not get any accuracy except for sort of tens of milliseconds. The accuracy of these clocks are in microsecond range, single microsecond range. Now, at this point, what you did see there is that actually, T-commit and T-start were retrieved from this hardware clock. That means that you can make accurate comparison about when transactions started and when they were committed. That is unique. There's almost no environment in this world where you can get this except into AWS. Now, let me be honest, by the way. As much as that I can say that these clocks are highly accurate clocks, actually do not truly exist. There is always maybe a slight drift. There's maybe a little communication difference. There is some delay somewhere. And as much there is an error bound on each of the times that you get. And we've built yourself a system. We built ourselves a system called clockbound. It's a daemon that runs on your EC2 instance, and there's a library that is in GitHub that you can make use of. That will give you not only the accurate current time, but the potential error bound around it. And you can make use of that error bound. You can think about what is the earliest time. And if this is the accurate time, actually what we think, but what could be the drift off, the earliest time, or what could be the latest time at this point? You determine which of these clocks you actually are going to take. So this actually doesn't give you microseconds, it actually gives you a nanosecond clock. And you also get the bounds in where we think, what is the potential error on this. And that's not bad. You can actually make use of this error bound to actually consider to be what is the most possible latest time that this happened at, and what is the earliest time. Now, both Aurora DSQL makes use, and it becomes extremely simple under the covers, because we can make use of synchronous time. And it's the same technology that we used in Amazon DynamoDB global tables that now also provides strong consistency. Much simpler. We can do worldwide strong consistency because we have access to synchronized time. Precise clocks reduce complexity significantly. Look at all these algorithms. I've worked on many of these because I never had access to time. Distributed transactions, conflict resolution, leader election, two-phase commit, Paxos, WAFT. All of these would be so much simpler if you just could use time. And I know Matt also started his presentation on Tuesday, but talking about how we always wanted to give you the building blocks for building the next generation of systems. And originally, really compute, storage, databases, network, and security. Those were the original building blocks. But now we've added a more fundamental building block to all of this. And that fundamental building block is time. I urge you all to look at sort of the algorithms and the mechanisms that you're building in your applications, and whether synchronized time can actually help you to significantly reduce the complexity of your systems. So that more or less are my lessons for today. Thank you for listening to all of this, and we all have time to spend, so I'm about to let you go. I am actually going to spend my time in the coming year about something that I actually want to raise your attention to. We, as you know, also if you've watched the Now Go Build TV series, I'm very passionate about younger businesses and organizations that try to solve some of the world's hardest problems. If you look at the sustainability goals of the UN, by 2050, we're supposed to have 2 billion more people on this planet. How are we going to feed them? How are we going to provide healthcare to them? How can we make sure that they have an economic, sustainable future? And there's many, many young businesses and organizations that are trying to attack these problems. And I really want to help them. So one of the things that we're doing is we have an organization called Tech to the Rescue, who have a cohort system for AI for change makers. And I've created a fellowship for their CTOs. So I'm helping them, and my team is helping them, sort of really beef up their technical capabilities. And I've been very grateful for the heroes actually also stepping up and helping to advise these young businesses how they can actually use technology to do good in this world. So thank you very much, guys. By the way, one of these things that these organizations tell me, they often have a very small unit of technologists. And what they could really use sometimes is just 2 weeks or a month of someone's time. If you are looking to do some good in your work and make use of your technology capabilities to really make a difference, start looking out these organizations and donate some of your time, donate some of your experience in building really big systems to actually truly make a difference in this world. As technologists, we created, not everything beautiful, but it's also our responsibility to actually solve some of the world's hardest problems using technology. Now, okay, the serious part is over. I'm going to spend my time tonight on actually going to this party. I hope to see you all tonight at the Las Vegas Festival grounds. Weezer and Zed tonight. So see you there. Party!